So the next question says, we're going to write the equation of a parabola given 3 points. It says, what's the equation of the parabola that passes through the points 2, -12, -1, -15, and -4, -90? Now, you could go ahead and put those points on a graph. However, that third one is kind of a problem in terms of like fitting it into a visible space. So what we're going to have to do is we're going to end up writing a system of 3 equations. So off to the side here, I just want you to say, write a system of 3 equations. And we did this back in chapter 1. But we need to actually come up with our system of 3 equations on our own this time. So what we're going to do is we're going to take our standard form. And so what the directions here, so write a system of 3 equations. We are going to plug in each x and each y into y equals ax squared plus bx plus c. So this is what we're going to do. Plug in each x and each y into y equals ax squared plus bx plus c. Once we do that with all 3 points, we will have a system of 3 equations, and then we'll be able to work through and solve our system. So go ahead and write that down. We're going to hop over to the example. We'll work through it, and then we'll have one more problem after that, and I think we'll get to use our graphing calculator for the next one. Yeah. All right. Anybody need more time on this over here? Cool. So for the first equation, we're going to have to write pretty small in order to get this all to fit. So first equation right here, we've got x and y. So 2 is x, -12 is y. So we're going to write -12 equals a times x squared. That's 2 squared. X is 2. Plus b times x, which is 2, and then plus c. So we're just plugging in -12 for y, and we're plugging in 2 for x, because that's what x and y equal. We are plugging in 2 twice because there's 2 x variables on the right side of this function. So then we're going to go ahead and write this in more of a standard form. So this is going to be -12 equals -2 squared is 4. And usually we put our number in front of the variable. So I'm just going to write 4a. And then this is going to be plus 2b. I'm going to put the 2 in front of the variable, plus 2b plus c. So that's our first equation there. Our second equation, just going to do a little line here so we can separate that out. We're going to use -15 for y and -1 for x. So we're going to say -15 equals a times -1 squared plus b times -1 plus c. So -15 for y, -1 for x. And then we'll keep the -15 here, and that's going to equal -1 squared is 1, and 1 times a is just a. So that's going to be a. B times -1 is -1b, or just -b, so minus b, and then plus c. So -15 equals a minus b plus c. And then finally, we're going to plug in -90 for y and -4 for x. So we'll have -90 equals a times -4 squared plus b times -4 plus c. And that'll give us -90. -4 squared is 16, so that'll equal 16a. -4 times b is -4b, so minus 4b and plus c. So those will be our 3 different equations for our system. So we need to review how to solve a system of 3 equations at this point. First thing I'm going to do is write all 3 equations one on top of the other. So I'm just going to take this equation and and write them both underneath this one. So let's just create another line here. I'm going to put a blue line above that just so we can separate this out a little bit. We'll have -15 equals A minus B plus C. And then we'll have negative 90 equals 16A minus 4B plus C. All right. So here is our system of three equations right there. Now, if we think back to chapter 1, in order to solve for a system of three equations, we first have to eliminate one of our three variables. So if you're looking at the variables there, A, B, and C, which of those three variables, I mean, you got a pencil? You got a pencil? You got the notes from yesterday? I got an extra copy. So we got our system of three equations. We need to go ahead and get rid of one of our three variables. Which variable of those three looks the easiest to cancel out? C, yeah. Those all have the same coefficient, it's all 1. So if we group up these two and subtract them, that'll cancel out C. Now remember, we have to do that twice. We have to group up two different pairs of equations to eliminate the one variable that we need to get rid of. So let's call this one equation number 1. That'll be equation number 2. And then here's equation number 3. And C is definitely going to be the easiest one to get rid of. So we're going to have to create a couple of pairs of two equations. So if we take like equation 1 and we subtract equation 2, that'll get rid of C. And then if we take equation 2 and subtract equation 3, that will also get rid of C. So we'll do those two things separately. So this one's going to be another line here. Negative 12 equals 4A plus 2B plus C. And then we're going to put that over negative 15 equals A minus B plus C. And what we're going to do with those two equations is we're going to subtract them. And when we subtract these, we just subtract them straight through. So we're going to start with negative 12 minus negative 15. So it's not negative 12 minus 15. It's negative 12 minus negative 15. That makes a big difference. So it's not going to be negative 27. It's going to be what? 3. Good. Positive 3. Negative 12 minus negative 15 is the same as negative 12 plus 15, which equals 3. All right. Then we're going to have 4A minus A, which will be 3A. And then we're going to have 2B minus negative B, which is the same as 2B plus B, which is 3B. And then C minus C cancels out. So we have one of our two equations here that has two variables. So we need to do that again. And so let's just group up equations 2 and 3 to get our next one. So I'll just do that down here. That'll be negative 15 equals A minus B plus C over negative 90 equals 16A minus 4B plus C. Once again, we're going to go ahead and subtract those two equations, because that will eliminate C, leaving us with just variables A and B, and then we'll have a system of two equations, and then we can solve from there. So here we go. Negative 15 minus negative 90. Positive 75. Good. So that's equal to 75. And then 1A minus 16A. 1 minus 16 is negative 15. So that's negative 15A. We have a negative B or negative 1B minus negative 4B. So negative 1 minus negative 4. 3. Good. Plus 3B. And that's it, because the C's cancel out. C minus C cancels. All right. Now, this is actually going to be a relatively simple system of two equations to solve, because I'm just going to go ahead and write our first two variable system underneath this one here. And that's going to give us, so it'll be 3 equals 3A plus 3B. And this is kind of convenient because which variable cancels out really easily on this one? B. Yeah, we got the same number in front of them. So once again, we'll just subtract those two equations. 75 minus 3 is 72. Negative 15 minus 3 is negative 18A. And then the 3b's cancel out. So divide by negative 18. What does A equal? What is it? -4. Good. So A equals -4. All right, so we got A equals -4. And then to figure out B, let's just plug in A into this equation here. Because that's got smaller numbers than the one with 75 and -15 and all that. So if we take our value of A, plug it in here, that'll be 3 equals 3 times -4 plus 3B. And then we can solve for B. So that'll be 3 equals 3 times -4 is -12 plus 3B. Add 12 to both sides. That gives us 15 equals 3B. So what does B equal? 5. Good. B equals 5. So we solved for our first variable. We plugged in the first variable into one of our systems of, or one of our equations with 2 variables and got the second variable. Now to get the third variable, what do we have to do? Yeah, plug into one of the 3 original equations. Now, which of those 3 equations looks like it's going to be easiest to figure out C? Probably the second one, yeah, because there's no coefficients in front of A or B. So let's use this second equation to solve for C. So I'm just going to do that over here. And we're going to have -15 equals, we have A, -4. B is 5, so -5, and then plus C. So let's see, -4 minus 5, that's -9. So that's -15 equals -9 plus C. -15 plus 9? What does that equal? -6. So C equals -6. All right, there we go. A is -4, B is 5, C is -6. What we are doing is we're writing an equation in standard form. So I'm just going to write y equals, once again, I'm going to write y equals ax squared plus bx plus c. And if you take a look, we have A. We can plug in -4 for A. We can plug in 5 for B. We can plug in -6 for C, and that will be our answer. So we're going to say y equals -4x squared plus 5x minus 6. That's the equation. So this is a combination of a whole lot of stuff that we learned both from this unit and from chapter 1. And of all the things that we have, in terms of the longest process that we've learned so far, solving a system of 3 equations is probably the longest process we have so far, out of everything we've done in Algebra 2 so far. Is it going to be the longest? At least for a while. Yeah, if I think ahead, I can't think of anything that takes up more paper space than solving a system of 3 equations. Now, the nice thing is the next one. Any questions here before we move on? The next one is entirely calculator based. So if you do not have a graphing calculator yet, go get one. Go pick up a graphing calculator if you don't have one in front of you right now. Because everything we're doing on this next one, we have to use a calculator for. Or I shouldn't say we have to, but it's going to be a lot easier for us to use a calculator. So grab a calculator if you don't have one. All right. So here's the thing. If we wanted to, we could do the same thing we did in the last problem. We could choose x, y, x, y, x, y, and solve a system of 3 equations with these fun decimals. But I wouldn't want to do that because the calculator can do it for us. So what we need to do, I'm going to read this and I'm going to talk about how we're going to make this happen. Now, you've already done some of this work using linear equations. And so some of the groundwork in terms of getting the information into the calculator you've seen already. So we'll practice that again. It's actually a very, very slight difference getting a parabola equation versus a linear equation. So there's not a whole lot of difference based on what we did in chapter 1. So a fan threw a souvenir football into the air from the top of the bleachers toward the bottom of the bleachers. The table shows the height of the football in feet above the ground at various times in seconds. If the football was not touched by anyone on its way to the ground, about how long did it take the football to reach the ground after it was thrown? So, first of all, we need an equation. So, off to the side here, I'm going to grab a copy of the All right. So off to the side, I want you to say, let's write this down. So graphing calc, write that on your paper there off to the side, graphing calc. So we're going to go to stat, edit, and we're going to enter the table values. Just like we did when we did our linear regression, we figured out the equations of lines. We're starting it off the same way here. So what I want for you to do on your graphing calculator, you're going to hit the button that says stat. That's right next to the left arrow. And then you're going to choose option number 1, which is edit. And if there's anything in L1 or L2, we need to get rid of it. So listen up. Go to stat edit. If there's anything in L1 or L2, you need to scroll to the top and highlight and then hit the clear button and then enter. That'll get rid of all the numbers in L1. Same thing with L2. If there's anything there, go up to where it highlights L2, hit clear and then enter, and that gets rid of the data. Then we're just going to go ahead and type in everything we have. L1 will be the values of X. L2 will be the values of Y. So time, those are your X values. Height, those are your Y values. So on L1, we're going to have 0, 0.2, 0.4, 0.6, 0.8, and 1.0, or 1. All right, then L2, 10, 11.76, 12.24, 11.44, 9.36, and 6. All right. Quick question for you. How high up in the air was the ball when the fan threw it? 10 feet. Yeah. Yeah, because at time 0, the fan had not yet thrown the ball, and it started at a height of 10, and it went up a little bit, and then it went back down. So it's basically starting here, it goes up a little bit, and then it goes all the way down to the ground. All right. Once you go to stat edit and you get all this information, you are then going to go to stats and then over to calc. And from there, you're not going to go to linreg, you're going to go to quadratic. So stat, calc, quadratic, which is option number 5. Because we're not looking for linear regression this time, we're looking for quadratic regression this time because we have a quadratic function as opposed to a linear function. So if you scroll down to option number 5, quadratic, hit enter. Just head all the way down to calculate and hit enter. And if yours looks like mine, that's fine. However, it's always a good idea to have the values of R, or in this case, R squared, because we're looking at quadratic instead of linear. So if yours looks like mine, where you don't have values of R or R squared underneath here, we need to go to mode. So if you don't have those extra values underneath A, B, and C, click the mode button. Scroll down to stat diagnostics, which is right here. Click on, make sure those are on. Then go back to stat, calc, option 5, quadrag. And then we'll have our values. And it gives you an R squared value of 1. So if you remember back to linear regression, what was an R value of 1? What did that mean? Yeah, it was a very strong correlation. It basically meant it was a perfect linear correlation, which means this is like a perfect quadratic correlation. So if we were to graph that, it would look like, I mean, those points on there would follow a perfect parabola. All right. Now, A, B, and C, it just gives them to us, which is really nice because all we have to do now, we've got A equals negative 16. We have B is equal to 12, and we have C is equal to 10, which is the y-intercept, which is the height of the ball before it's thrown, 0, 10. That's that right there. So we're going to write our equation. We're going to say y equals negative 16x squared plus 12x plus 10. That's the equation. That doesn't answer the question being asked, though. Let's go back to the problem real quick. If the football was not touched by anyone on its way to the ground, about how long did it take the football to reach the ground after it was thrown? How do you think we could figure this out? Listen up. How do you think we can figure this one out? How long does it take the football to reach the ground after it was thrown? Any thoughts on how we can do this? Let me ask you this. How high above the ground is the football when it hits the ground? The height of the football is 0. Yeah, when it's on the ground, it's 0. Is height X or Y? Height is Y. Okay. So we are going to use some future lessons to talk about how to solve for X, which you did back in Algebra 1, but I'll hold off on that for today. What I'd like for you to do, though, is go to your Y equals menu, and we're going to graph. So type in this equation, negative 16x squared plus 12x plus 10. And then go to your graph. There's our parabola. Now, in terms of where the fan threw the ball, it was thrown here. Threw it from the bleachers. So if X is time, this is negative time, so that's not a thing. So the time actually starts here. Throws it up. Time is about, that's where it ends up landing. Right here. When Y equals 0. Now your calculator will actually tell you what that number is. So here we go, you ready? Once you have your parabola, find where it says calc. It's at the top menu here where it says trace. There's calc written in blue right above it. So hit the second key, the blue button, and then hit trace to get up to your calculation menu. And what we are looking for is when Y is equal to 0. And on your calculator, that is called a 0. So we're calculating a 0 of that function. And the 0 that we are trying to calculate is the one on the right, not the one on the left. There are two zeros here. There's one here and there's one here. We want this one because that's positive time and that makes sense. Negative time doesn't make sense. So at the bottom, it's asking a question. It says left bound, question mark. A left bound, it just means you're making a boundary around where you're trying to figure out that point. So if you push the left arrow key, you'll notice it'll go up, it'll leave the screen, but then it'll come back down. You can see it kind of flashing here and here. We want to be on the left side, or I guess in this case, above the x-axis. We want to be on the left side of where that Y equals 0. So right about here is great. So you can hit, once you get to the left bound right around there, hit enter. And then it's going to say right bound. And then you're going to keep scrolling to the right until you're underneath the x-axis. So there's our right bound there. We're just finishing up the notes from yesterday. So you've got a right bound here, and then once you have that, hit enter, and then it's going to say yes. It's just going to give you an approximation of where that point is. So hit enter one more time, and we should have an answer of 1.25. So it says x is equal to 1.25. So when the ball hits the ground, when Y equals 0, the time it takes for it to do that is 1.25 seconds from an initial height of 10 feet. So we would say it takes 1.25 seconds. That's our answer. All right. So last question down here. We'll just talk about this very last question. When we turn the page, there's going to be some, well, I might ask you a couple of the questions from the back. We won't do a lot more writing. I want you to be able to get onto your assignment. So it says, how many points does it take to determine the equation of a quadratic function? What types of things did we do in this lesson, and how many points did we use to figure out the equation of the function for quadratics? 2, yeah. We did 2 definitely back here yesterday. If you have, where did we talk about that? I guess we did that with the 2-1 lesson. If you have the vertex and a point, those 2, you can write the equation in vertex form. How many points did we use today, though? 3, yeah. So either 3 random points to write the equation in standard form, or the vertex and another point if you want to write it in vertex form. So those are kind of your options on how many points you need to write a quadratic function. Why do you think there were so many more points used in the table on problem number 5? Why was there so much more information here than just 3 points? Why do you think? Any thoughts on that? No? Right. That's okay. If you have a function and you have points that are super close to each other, 0, 0.2, 0.4, if you were to use like these 3 right next to each other, calculating a parabola might be kind of challenging because there's not a lot of information, and it might appear to be more linear between those 3 points because 10, 11.6, 12.24, those are all going up, right? So that might look more like a line. And so we need more information here to say, oh, it actually starts going down on the opposite side. So the more points we have, the more accurate we're going to be able to be with calculating a parabola. So if you were using, by the way, if you're using 3 points on this one to actually figure out the equation of the parabola, I would not use 3 that are right next to each other. I'd probably use the first one, some other point over here, and then the last one. Spread out those points as much as you can, just so you can figure out if it's going up and then down and how steep it's happening. But when the points are that close together, because the biggest difference between x values here is 1. From here to here is only a difference of 1 on the x-axis, which is not very much. So those points are so close together, getting the details will be very tough with only 3 points. And so that's why we've got 6 points for the calculator to figure out in more detail what that equation is. All right, flip it over to the back. So this is what we worked on yesterday. What key features can you determine about a quadratic function from an equation in standard form? We don't need to write this down. I just want to kind of discuss and recap what we learned about. So that's that y equals ax squared plus bx plus c. What did we do with that yesterday? Shh, listen up, guys. What did we do yesterday with that equation? We just took notes on it yesterday, and it was like right over here. What were we able to figure out from standard form? The axis of symmetry, the vertex. What else? There's a value. There's a value in that function that is a specific part of the graph. That would be the axis of symmetry. Oh, what's up? Yeah, yeah. So we got the vertex, right? Axis of symmetry. What else can we figure out from standard form? The y-intercept, that's the value of c for sure. Can we look at a standard form equation to figure out if it faces up or down? Yeah, the value of a also, right? A determines whether or not it's right here, same as vertex form for a. So that means if it's facing up or down, if a is negative, it's upside down. If a is positive, it's right side up. Can we look at a standard form equation and know if there is a vertical compression or stretch? Yeah, value of A also determines that. So there's quite a few things in terms of key features that you can determine from the equation of standard form. How about this? Amos says that the y-intercept of a quadratic function always tells the maximum value of that function. It says error analysis, so we know that's wrong. Why is that wrong? Why is the y-intercept not always the maximum value? Yeah, well, that and the fact that the maximum or the minimum of a quadratic function is what point of the function? It's the vertex, yeah. Sometimes the vertex and the y-intercept are the same thing. Most of the time it's not. So I'd say the error here is the fact that, first of all, we don't know if it's facing up or down. And the maximum value is the vertex, which isn't necessarily the same thing as the y-intercept. In fact, most of the time it's not. How about this? Last one here. This is what we did, first question of the day that we did today with our system of three equations. Why do you need at least 3 points to graph a quadratic function when not given an equation? Why did we need 3 equations and 3 points on example number 4? Yeah, and we've got xy, right? Xy are just xy coordinates that we were able to plug in. We needed 3 equations because how many variables are here when you plug in for x and y? 3. If there's 3 variables, that means we need to figure out the value of each variable, which means we need 3 equations to write a system of 3 equations to figure out what each variable represents. So however many variables are in an equation is how many equations you need in order to solve. So that's why for that. All right. So that's all I got for you for lesson 2. So for the rest of the day today, you will be working on the assignment.